of another planet. So 12 instruments, but the reason that Cassini is near and dear to me is because I spent most of my undergraduate working with the science team of this instrument here, which is the main camera suite of the Cassini mission. All of the, I wouldn't say all of the beautiful images you see of Saturn, but most of the beautiful images that you see of Saturn are from these instruments. And most of these instruments can be grouped in several different ways. The main one is two of the instruments use radio waves to do their science. They bounce radio waves off of objects in the Saturn system to get an idea of what's beneath the clouds of, say, Titan, for example. Then we also have the main camera suites and spectrometers, which first of all produce very pretty images, but then they also tell you something about what things are made out of without having to actually go and touch the thing to figure out what it's made out of. And then the last group of instruments looks at the magnetic field and the particles and stuff like that in the space environment around Saturn. So in terms of the timeline, the Cassini mission launched in '97, so I was in second grade when it launched. It got to Saturn in 2004. I was a sophomore in high school when it got to Saturn. Shortly after that, that's when it launched that probe off of it, Huygens, which then landed on the surface of Titan, Saturn's really large moon. Titan is larger than Mercury, by the way, if anyone's counting. And then it was around Saturn doing a lot of good science until last Friday. And here I am just starting a postdoc, having gotten my PhD. So that gives you an idea of the length of the Cassini mission. So from launch till death, it was about a 20-year-long mission. So lots of time, lots of science. So what I'm going to show here is a video that was made by a Dutch director that used only footage from the Voyager and Cassini missions. It's mostly of Saturn. It also has some gratuitous Jupiter in there, and I'll try to give you some warning when Jupiter comes about. So let's go ahead and start this. So first we're looking at the rings of Saturn. These are this is actually from the Voyager mission to start with. And this video is available online if you decide you want it later. So these are looking at the rings, more rings. You see those spokes in the rings, and then you're seeing different angles to the rings as it's going around. So this is sort of looking at different lighting geometries on the rings. So you're looking at above the rings to then as the spacecraft passes below the rings, and there's a moon just randomly orbiting there. So there's another moon. They also found particles and ringlets. And this is actually geysers off of a moon of Saturn. And that is a moon interacting with one of the rings, showing the orbits of the ring particles around Saturn. They're showing different lighting geometries too. Okay, so this is the gratuitous Jupiter stuff. Okay, that was Jupiter. These are moons of Saturn. That's Saturn at different wavelengths. That's actually showing methane clouds. Here's some more gratuitous Jupiter. Sort of compare the storms on Jupiter to the storms on Saturn. So these are showing little eddies in Saturn's atmosphere. These are showing moons orbiting the rings and showing wakes in the rings. And these images are not manipulated, by the way. These are just raw images from this spacecraft. More moons. Saturn has a lot of moons, so we're going to be looking at a lot of pictures of moons. Saturn has about 62 named moons, and then there are quite a few other little guys that don't get names. That's also a moon of Saturn that's slowly rotating. So that's sort of an introduction to the Saturnian system. Also, sometimes you'll see it listed as the Cronian system, because Cronus is the other name for Saturn, so the adjective that sometimes people use is Cronus. But in terms of what, in order to accomplish all the science and get all those cool pictures, the Cassini mission did not just have one constant orbit around Saturn. It varied quite a bit. It had quite a few flybys of Titan, and also some of the other moons of Saturn, including Enceladus, which is that one with the big geysers coming off of it. And the Saturn year is about 30 Earth years. So Cassini was able to witness the changes in season on Saturn to some extent. Not a full year, but to some extent. So that's what that's showing at the bottom. So if you look at sort of an orientation of the Saturn system, the closest stuff to Saturn is the rings, basically. And then as you get further out, you start getting larger moons. There are some moons in the rings, but they tend to be those small, sort of potato-shaped guys that you sometimes see that look sort of like asteroids. But then as you get further out, you start getting to larger moons, and then way out, not even on this picture here, you have Titan, which, as I mentioned, is larger than Mercury. It is the largest moon in the solar system, actually. And in terms of main science results out of this, we were able to observe the interactions between moons and rings in real time. We actually, as you saw in those videos, you could see the wakes that would happen in the rings as the moons orbited around, and you would see these over the course of hours, because the orbital periods of these moons around Saturn are, some of them are even less than a day. So you could do a lot of science looking at the gravitational interactions between the rings and moons, and even non-gravitational interactions like static charges and stuff like that. The other science that came out of this was showing that the ring particles are not all one size. They're not all, really tiny particles. Rings are clumpy sometimes. In fact, that arrow that's showing is sort of cut off there, but there's a moonlet embedded in the F ring, for example. So it's not quite large enough and massive enough to clear its own gap, but it perturbs the particles around it, so you get these clumps in rings that you can see orbit around. In terms of moons, some of the moons are a lot more active than we thought they should be. So the moon Enceladus is actually smaller than the United Kingdom, a balmy minus 300 degrees Fahrenheit. But that temperature is about the same temperature as the triple point for methane. And we know here on Earth that the average temperature on Earth is right around the triple point for water. And so we have rain, we have oceans, we have evaporation, we have a lot of different weather. And so there was some thought that maybe Titan would have something similar, maybe not with water, but with methane. And it turns out that Cassini not only confirmed this, but also observed it in action. They actually even observed changes in the surface. So what I'll show here, so these are looking at changes on the surface of Titan. So this is radar images looking through the clouds on Titan. And this dark area here formed right after a rainstorm of methane on the surface. We even saw sunlight glint off of the lakes of Titan, so that's what this blob is here. So this is the haze layer of Titan, and this is the glint of sunlight off of one of the lakes in the North Polar region. And from a geologic perspective, we also saw features that were very similar to what we see here on Earth with river networks and estuaries. Except on Titan, it's cold enough that water ice behaves like rock. So the mountains and pebbles and stuff like that on the surface of Titan are mainly water ice. But the liquid is methane and ethane, so this sort of hydrocarbon soup. Methane is also one of the things that farts are made out of. So whenever I do outreach at schools, a lot of times people ask me about that farty moon, the moon that has lots of farts on it. And I'm like, well, there's nobody there, so there's nothing farting. But they still call it farty moon. Okay, anyway. So those are some of the moons. As with any exploration, we always find weird stuff also. As we image these moons at high resolution, they were pretty strange. We have an impersonator of a Death Star, Mimas. We also have some moons that actually had a lot of dark material deposited on them. So this Hyperion, that's why it looks so spongy, is because it has a lot of dark material that's been deposited in craters, and so it looks very spongy. And it is actually statically charged. It's the only other object aside from our moon that we know that actually has a static charge to it. Why? Who knows? We don't know. Iapetus is an example of a very icy object that has been painted with dark material from impacts from another moon of Saturn. And this one also just has a weird shape. This is a moon that orbits really close to one of the rings. And it kind of looks like a flying saucer, which is reinforced by the fact that a lot of these images are very blurry and shaky. But it kind of has the shape of one, so that basically along its equator it has this sort of weird bulge of material. which actually shows that the rings and the tiny moons near them interact a lot more than we thought that they did. So Cassini was in fact not orbiting the moons, but it was orbiting Saturn, so it did do some science around on Saturn as well, particularly the dynamics of Saturn's atmosphere. So showing just a few things here. There's a hexagon at the North Pole of Saturn. What does that mean? We don't know. It's shaped like a hexagon. Why? We don't know. It's probably some type of standing wave in Saturn's atmosphere, but why the North Pole has one and the South Pole doesn't, we don't know. You can, if you get a sort of disk of material and you rotate it, you can actually, in just a physics lab, make standing waves. Maybe not hexagons, but you can make squares and that type of thing. But we don't know quite why it's a hexagon. So that's one thing. The other thing is, I mean, Jupiter is of the gas giants, Jupiter is known for having big storms on it. You know, we hear about the red spot, we hear about very large storms. Saturn's atmosphere comparatively is a little bit more bland in terms of color, but it does have storms, and in fact we observed a storm on Saturn that developed, so that's what this sort of white feature here is that's sort of bellowing across, and it actually progressed so that it wrapped completely around Saturn, which has not been observed on any other gas giant in the solar system. We don't really know why it would happen on Saturn as opposed to Jupiter, but we did not observe anything like that on Jupiter. So that's another thing that Cassini has observed. But all good things must eventually come to an end. And so eventually the mission, Cassini mission, had to end. So why is that? The main reason is that it was low on fuel. To change its orbits, all those orbits that I showed, it has to expend fuel to do that. And it was low on fuel. And once it runs out of fuel, we can't really control the spacecraft that well. It would have continued to orbit Saturn, but especially with the discovery that Enceladus had a lot of ingredients that would be important for life, a lot of people were talking about trying to have the spacecraft not crash into that. In order to be able to do that, we have to be able to control the spacecraft, which we can't do when it's low on fuel. So they wanted to avoid having any chance of it impacting Enceladus in the foreseeable future because they didn't want the spacecraft to destroy that environment. One of the main reasons they chose to then send it into Saturn is because in doing that, they can actually do a lot of unique science that they would not be able to do otherwise with that mission orbiting Saturn. So as far as the timeline of its demise, which happened last Friday, it did a distant flyby of Titan, and then about 16 hours or so before it actually was sent into Saturn's atmosphere, it took its last image. Then it downlinked as much as it could off of its data recorder. And then it was basically put into streaming mode, where it was in real time streaming the data it was taking. So it wasn't recording, it was just streaming it across the deep space network. And then eventually on very early Friday morning, it then went into Saturn's atmosphere and burned up. So that's the timeline of what happened. So the impact site in the clouds this is an infrared image looking at the cloud bands of Saturn. So these are bands of clouds across Saturn's, I shouldn't say surface because it's a gas giant, but across the surface that we see of Saturn. And this little ellipse here is where it actually impacted the clouds. But keep in mind that it took its last image many hours before it actually entered Saturn's atmosphere. And this was the last image that it took. So what you're looking at here, it's kind of washed out on the screen, but this is the day side of Saturn, this is the night side of Saturn. These stripes at the bottom here are actually reflected light off of the rings of Saturn. But this is the night side. And you can see some sort of little eddies in here if you're close enough. But that was the last image that Cassini took. So the instruments that were actually on when it went into the atmosphere were not the cameras. And there was actually a good reason for that, because cameras are data hogs. They take a lot of data. And in order to be able to, a lot of the instruments that would actually study what the atmosphere was made out of, get detailed information about the gravity field of Saturn, stuff like that, are not the cameras. So it makes no sense to have the cameras on. So they didn't have the cameras on, which is why you don't see, press images of like the video of Cassini dying. I mean, that's sad, but it's also because there was a practical reason for that. So most of the images that were, or most of the instruments that were turned on were magnetometers, the radio instruments to get very detailed telemetry information, so how fast the spacecraft was going. So that tells you something about the atmosphere that it's going through. So those were the instruments that were on. So the last few orbits that Cassini did around Saturn, it did skim the top of Saturn's atmosphere. So those are what these dots are here. But keep in mind, it came screaming through the atmosphere at 30 kilometers per second. So that's the equivalent of going from New York to LA in less than 2 minutes. So it's going very fast. And in fact, Cassini is not the first thing we have sent into a gas giant. We sent a Galileo probe into Jupiter. But the Galileo probe had a heat shield on it. Cassini did not. So the Galileo probe going into Jupiter lived for about an hour as it was going down. And it was actually traveling faster than Cassini was going into Jupiter. It was traveling at about 45 kilometers a second, whereas Cassini was traveling about 30. But Cassini had no heat shield. And so as it was going through the atmosphere, eventually it will start tumbling in the atmosphere and lose line of sight with Earth, which is when we lost contact with it. And then after it starts tumbling, then it's going to start breaking up, and instruments are starting to heat up. So there are probably some of the instruments that were made of materials that were higher melting points that probably survived for a little bit longer than this loss of signal altitude. But overall, between the loss of signal and the time the spacecraft probably broke up was only about 10 or 15 seconds. So heat shields make a huge difference, moral of the story. If you want to go into a gas giant, bring a heat shield. So by the numbers, Cassini was a 20-year mission. It spent 13 of those years around Saturn, so had a lot of good science done. A lot of data collected, so 635 gigabytes. And for people who do stuff with LSST or some of these big, very large surveys, that may not seem like much, but as far as planetary missions go, that is a large amount of data that you're beaming out from the outer solar system. Almost 4,000 science papers published from this data. About 27 nations participated. The U.S. paid about 80% of the cost. The rest of the cost was with the European Space Agency and the Italian Space Agency. And as far as the cost goes of all this data, it cost a little less than $4 billion. So this includes pre-launch as well as the 20 years of ops. So if you usually don't think in those terms of those numbers, I know I don't. That's the equivalent of 3.5 football stadiums for the Minnesota Vikings, in case you're wondering. That's also the equivalent of less than 1% of the amount that the U.S. military spends in 1 year. But it directly employed over 5,000 people. What you're seeing here is some of the members of the Cassini science team from the different instruments. And when I say directly employed, this number doesn't include people like me that did a lot of research with and collaborated with members of the science team, but were not members of the science team themselves. And as I mentioned, nearly 4,000 science papers published, and it just stopped taking data, so there's likely a lot more papers to come in analyzing all of the data, because there's still a lot of data. So with that, I will take questions. Thank you.
What, in your opinion, is the most significant science result of Cassini?
What, in my opinion, is the most significant science result of Cassini? I would say probably the fact that the Saturnian system is in a lot more active place than we thought it would be. Saturn is in the outer solar system. Stuff is cold. Saturn itself is kind of cold. So naively going out there, you would expect that the moons aren't very geologically active, that there's, yes, there are rings, but, what else? So especially the results about Enceladus are definitely new. And also the detailed observations of Titan and the weather on Titan. but everyone has their pet moon of Saturn. Hopefully I've convinced you that objectively Saturn is the best planet of all of the planets. It has it all. It has rings, it has moons, it has atmosphere. Maybe it has life, we don't know. Yeah.
So the Cassini was crashing with Saturn because you don't want to contaminate the other moons with contaminants from Earth. What about the Huygens probe, which did land on another moon, and we've sent rovers to Mars, we've sent things to Venus. What kind of precautions have we taken in those cases to prevent contamination? And I guess, did we not do that with Cassini, or was it not sufficient enough with Cassini?
So I think the issue in terms of planetary protection, because that's what that whole field is called, is planetary protection, is we did try to sanitize the rovers to some extent. There have been actually some issues with that in the sense of some of the measurements of methane on Mars. People have been wondering about whether that methane that the instruments were measuring was actually methane that was sort of stuck in the instruments from Earth, as opposed to being Mars oriented. So not really contamination for bacterial life on Mars, but more gases that are from Florida. Florida's a very swampy place, lots of methane. So that's one. The other thing that they were concerned about with Cassini is that, keep in mind that the speed that Cassini is going compared to the moons is pretty high. So if it's not like you could sanitize the the spacecraft as much as you want, but if it slams into the surface of Enceladus at many kilometers per second, it will damage the surface, and we don't necessarily know how thin that shell of ice is compared to the subsurface ocean in some of those places. So that's the concern. Oh yeah, so maybe what really killed the dinosaurs was a spacecraft from somebody else. No. The spacecraft is too small for that. That was the KT impactor was a bit larger than Cassini. Any other questions? Yeah.
Did the team hope from the beginning that the spacecraft would last this long and have plans, or was it pretty surprising that it lasted?
So the question was it surprising that Cassini lasted this long? Well, I mean, what powered Cassini were radioactive, were plutonium-238. So it was actually, from a power perspective, it was going to have the power. In terms of the propellant, they planned very well throughout the mission to not expend unnecessarily large amounts of fuel. So they suspected that it would last this long unless there was some hardware failure on that part. Keep in mind, Cassini is also the largest amount of radioactive material we have ever launched into outer space. There's a lot of plutonium-238 on Cassini. In fact, so much so that for a while there were quite a few people that were concerned that when it launched, that if something happened to the spacecraft before it left Earth's orbit, that it would cause a lot of problems for people on Earth, which was actually not really a concern, but sometimes people ignore science. Okay.
Can you explain to the ignoramus why that's not a concern?
Well, it was a concern in the sense that if a rocket, say, it got to some altitude in Earth's atmosphere and then blew up and then spread a lot of radioactive material. Keep in mind, by a lot of radioactive material, this is still far lower than like a Fukushima event or something like that. So, yes, statistically speaking, it would increase the amount of cancer that people would have, but it's not going to be. I think it would increase the chance of getting cancer by far less than 1%. Far less than 1%. I think like 0.1% or something. So I think we would be more concerned with like Fukushima or Chernobyl type of events, which have nothing to do with exploring space. Any other questions? Okay, thank you for coming.
All right, so thank you everybody for another successful Astronomy on Tap. We will be having another event in October. We don't have the date lined up just yet. So I would encourage you to go onto Facebook. You can find our page there. You can like us, do whatever it is you do on Facebook. And I guess we'll hope to see you next month. Also, one last plug for the donation boxes up front for future trivia prizes. And okay, now I think that's all I have to say. So thank you again for everybody coming, and I hope to see everyone next month. Thanks.
that guy still in question?
Like what the best moments stuff like that,
I like my house. I know what it is, right?
I guess.
Hope you enjoy your soup. I ate a bunch of pizza now, so maybe I'll have it for lunch tomorrow. You had second dinner. Like,
yeah, so either a t-shirt or